let's get started with this course. This is perhaps the most abstract course in the whole curriculum, but I think one of the most fundamental courses for any computer scientist to know. Now, the really interesting stuff in this course is not going to help you write a program per se, and it's not going to help you build a computer per se. But it'll help you understand a lot more about what people have thought about in the last 50 years about computer science as a science. And it's about what kind of things can we really compute mechanically, how fast can we do it, and how much space does it take us to do it, how much memory does it take us to do it. And because of that, the course is called Theory of Computation. So like lots of abstract courses and courses that have a lot of really cool thinking and neat stuff in it, especially in computer science, there are lots and lots of applications that come out of this course, things that are pretty much serendipitous. All of compiler design and theory about building compilers and writing programs to translate languages comes from theory of computation. And not a direct application either, but more kind of a side effect. It turns out that some of the models of computation that we discuss happen to correspond to programs that help us write compilers. And there's lots of other applications as well. When you talked about computer architecture, you modeled a particular processor with a finite state machine. The idea of a finite state machine originally comes from theory of computation. When you do any string searching in any word processor or any kind of editor, that uses a finite state machine. When you do any kind of compiling or representation of a language like XML, you describe it with a grammar. And that grammar is the next level of model of computation. So what this course talks about is different models of computation, different kinds of things you can use to compute stuff. Now, what does it mean to compute something? In this class, it's going to be something very, very simple, because we want to abstract it all away from all the specifics of the machine and all the specifics of problems you see. So we abstract it away in this style. We imagine that all we're doing is dealing with programs or computations that take an input, somebody sends it an input, and the program sits and stares and thinks and calculates and computes, and then says yes or no. Do I accept this input or I do not accept this input? No actual number crunching or anything like that. Whatever number crunching involved is all in order to decide yes or no. So in order to do that, we simply think of things we want to compute as a set of things. And normally, the things are very simple. We pick an alphabet. It can be as simple as a binary alphabet. And it could even be a unary alphabet, just one symbol. And we consider strings along that alphabet. So what's an example of something you might want to compute? Say, the set of binary strings. That means strings over the alphabet 0, 1. That end in 0. Not a very hard thing to compute. Somebody gives you a binary string. If you're a human being, you look at the end of it, you see if there's a 0. If there is, you say yes. If there's not, you say no. You could all write a computer program to do this, certainly. You could have probably done it, some of you, before you came here. It's a very easy program. You look at the end, you see if there's a 0. There are other things that are harder. What if you took a piece of Java code and turned it into a binary file and wanted to know whether that really came from a legitimate piece of Java code or whether it's just some junky binary file that represents something else? Does this binary file represent a legitimate Java program or not? So we can write the set of binary strings that represent legal Java programs. So can you do that? Can you write a program that does that? I don't mean you personally. Could somebody write a program that does that? They better be able to. Otherwise, when you write your Java program and you say run this, what checks that it's a legitimate? What's giving you all those error messages, right? It's not some little mouse sitting in the machine saying, that's not right. Error on line 32. Or there's a program that looks at this and that does it. And it does more than just say yes or no. It actually spits out output. That's what compiler design is all about. So that you can still do, but it's a lot harder computation than that. And let's go one step further. The set of binary strings that represent legal Java programs that never infinite loop. That's probably not English, but you know what I mean. Loop is a verb there. That never go in an infinite loop no matter what input you would give them. Is there a program that will look at your Java code and tell you that, yes or no? And the answer is there isn't any such program. It's impossible. There's no way to compute this. No matter how hard you try, it's not going to work. It's going to either give you the wrong answer or it's going to run forever and never give you any answer. Your program that you try to write to do this doesn't exist. So that's what we're talking about in this class. What can you compute and what can't you compute? And what kind of models do we have to do this computation? Your own sense of how you do computation now is a programming language. You know Scheme, you know Java. That's one thing. We're going to abstract all those details away and get down to the root of what a programming language really is. And maybe the most popular way to view a programming language with everything stripped away is called a Turing machine, invented by Alan Turing. And it's a very simple machine. We won't talk about it yet today. We're going to build up to a Turing machine. But Alan Turing in the might have been the 1940s when he invented this. He died in the 1950s. Invented an abstraction, a mathematical abstraction that he thought was a complete representation of how we might do computation. To the extent that anything that you do on a normal computer with a normal programming language could be done on his machine. You could write a program for his machine that does the same thing. And his machine's very, very abstract and simple, but because of that, we can prove really interesting things about it, like the fact that this can't be computed. So what we're going to do in this class is work our way up from a much lower level. One thing when you define something abstractly is, here's a nice Turing machine, it's got arms, it's got legs, it's got a brain. What if I cut off its left arm? Can it still do everything it could do before but just take a little longer? Or is it actually handicapped and it can't do certain things that it used to be able to do? For example, the set of binary strings that represent legal Java programs. I know that I can write a program to accept those. Therefore, I'm sure I could write a program for a Turing machine that would accept those. But what if I cut off the Turing machine's left arm, metaphorically? Is it possible that I can't do this anymore? And I'm cut back actual power. Or maybe it just takes me longer to do it. Those are the kind of questions people ask in this class, in this course. That's the kind of questions scientists wonder. How much can I chop off of a Turing machine and still be able to do it? And then we're going to abstract it out. We're going to start with the lowest level, which is a finite state machine. And we're going to work our way up, building pieces on it until we get up to a Turing machine. And then start exploring the twilight zone, which are problems out here which can't even be computed by a Turing machine. Right, so that's the big picture. Are there questions about that so far? Little bullseye. One more. The simplest kind of machine we're going to consider is one that doesn't have as much power as programming languages. One that's simpler, called finite state machines. I'll abbreviate it, FSM, finite state machines. And you've seen these before, and you've seen their applications before. That's the smallest, simplest level. They can compute certain kinds of sets. They can decide certain kind of things, like whether there's a 0 on the end of a string. But they can't do things more complicated, like figure out whether something's a legal Java program. There's a lot of other things they can't do also. There's a lot of interesting things they can do. Outside of this, if you add on some power to the machine, is a class of sets that can be recognized by a more powerful machine. And those sets are called context-free languages. A set of strings is often called a language, not at all to be confused with a programming language. A language is nothing more or less than a set of strings. So the set of strings that have zeros at the end of them, that's a language, and you can recognize it with a finite state machine. Context-free languages are languages that are more complicated than the ones that can be accepted by finite state machines, and they also include the finite state machines also. So they're a larger group. All the stuff about compilers, legal Java programs, all those sets of strings, those languages, they're inside here. So legal Java programs are in here.
Context-free language?
In context-free languages. Then we bump up another level to Turing machines. That's full-level computation. That means anything that can really be computed with a computer, with any normal programming language, can be computed by these machines. So this includes everything that you know how to do. And way out here in the twilight zone,